After the general uncertainty principle, let's switch over from discrete space to continuous space. For example, position space. When we measure position of a particle or an object, suppose it is x equal to 2 centimeter, and at some later time, suppose it is at x equal to 3 centimeter. But between 2 and 3, there are so many continuous values of position which the particle can reside at, if we think about classically. Now, in quantum mechanics, what is position space? It is defined as a set of basis vectors in a vector space which can be obtained, which can be designed by the eigenstates of position operator x. There is an alternative space also which is called momentum space, and like position space, momentum space is also designed by the eigenstate of the momentum operator. Now, if x is the position operator and it is acting on this x ket is the eigenstate or eigenvector of the x operator here. We get eigenvalue x, this is continuous, and the eigenstate of the position vector itself, that is x ket. We assume that these eigenstates x are normalized, that is their length is equal to 1. So when we are switching from discrete to continuous space, in discrete space we have operator d acting on state di. I am getting discrete eigenvalue di and the eigenstate di ket. But in continuous space, this is the operator x which is acting on this eigenstate of the position operator x ket, and the continuous position value x can be obtained. The completeness relation in discrete space looks like this. This is outer product of two eigenstates di and di. If this is written like this, this is called outer product, and if it is written like this, this is called inner product or scalar product. This is the completeness relation, and this becomes like this, that is integration of minus infinity to plus infinity dx, and the outer product of x states, this is equal to 1. And this is the orthonormality relation for discrete space, and in continuous space we have this orthonormality condition. Let's define the probability also in both discrete and continuous space. Probability of finding a system in a discrete state di, in a state di rather, is defined as a scalar product of di and arbitrary state psi. I'll make a mod square of it and I will get the probability pi. As we are in discrete discrete space, so I am writing this as pi. And for continuous space, the thing is the same, the definition is the same, but now the pi has to be written like this, px dx. That this tells me about the probability of finding a particle or a system within this dx domain. That means if I have a position x and if I have a position x plus dx, then this px dx will give me the probability of getting a particle or a system within that position between x to x plus dx. This is a component of psi in position space, and as it is continuous now, so I write it as a function as we write fx in algebraic functions. And this is as usual a complex number, because components are complex number now in both discrete and continuous space. And this definition is called Born interpretation. And this psi x is now a complex function, but the function is of a real variable x. So if I make a complex function of the real variable x, I will get this psi. This x psi, that is scalar product between the eigenstate x and arbitrary state psi, this is called component of the arbitrary state psi in the position space. In discrete space, I have written the components like this. This is my state and this is my component. As we are in discrete space, so I have taken this summation sign, which runs from I equal to 1 to n, and I takes only discrete values. But here in continuous space, this summation sign will become integration sign. And this relation becomes this. Because integration dx and the outer product of x with x itself is nothing but the identity as we have just defined. So here in position space, in continuous space, psi and arbitrary state is written as integration of dx, then this complex number psi x and the state psi itself. As I have switched over from discrete to continuous space, I need to make a switch over, a transformation from summation to the integration sign. And the integration runs from minus infinity to plus infinity. Now let's see how the operators in continuous space like position operator and momentum operator operates on arbitrary state psi. As we are in position space, so this bra vector had to be written x. If we are in momentum space, instead of x in the bra notation, bra vector, we need to write p here. I will be discussing in a short while. So in position space, x operator, which is sandwiched between eigenstate x and psi, will give me this. And if it's p operator, I will get minus I h cross ddx of psi x. I will need these two relations, these two assumptions in future. Let's come to another continuous space, which is momentum space. In momentum space, we have lots of eigenstates. The entire space is designed or fabricated by the eigenstates of the momentum operator P itself. The eigenvalue equation in the momentum space looks like this. P is the eigenvalue, which is of course continuous now because we are in a continuous space. This is orthonormality condition. And for any function fp, I can write this. Completeness relation in the momentum space looks like this. And the wave function, which is component of psi in the momentum space p, is psi tilde as a function of p. Why I have written psi tilde? Just to distinguish between momentum space and position space. This is just a variance in the notation and nothing else. I have written the relations in a comparison form so that we can easily realize, understand, and we can easily memorize this. And this is a comparison of how we write the wave functions in basis independent form. In basis independent form, we write it as psi, and in position or momentum space, we write it as like this. These are functions because in these two spaces, we are in continuous space. This is another vector 5 which I obtained when I operate an operator x on psi, I get phi. And here in position and momentum space, if we operate psi on psi x, I get phi x, which is to be written like this. And the component of phi in momentum space should be written like this, because this is the momentum operator itself. This is components of the wave functions, psi x, psi tilde p. These are complex numbers. Here I have also written what we have learned so far in both position space and momentum space. When we operate p operator on psi, we get another vector, another state, which is called chi, and component of chi in position space, as I am in position space, so this bra vector has to be written x. If I am in momentum space, this is to be written p, just I have written like this here. So chi is my new state, new function, and component of chi in position space should be written like this. And these are the relations in position space. In momentum space, the similar relations will look like this.